Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Sample problem 5.2. The statement of problem is that the structure shown is constructed of W10 by 112 rolled steel beam. Draw the shear force and bending moment diagram from the beam and given loading, and the part B is determine the normal stress in section just to the right and left of the portion. So W is the wide flange beam, that is 10 by 112. You can take the properties of W10 by 112 from the appendix C that is given at the end of the book. So from that appendix C, you can take the value of Ix. You can also check the height, width and breadth of the beam, thickness of flange, etc., etc. So as we know that sigma m is equal to mc over I. So I value can be taken from that table, and if you know the cross section of the beam, so you can also calculate the C, distance from neutral axis to the topmost. So you can calculate, take this value from the table available in appendix C of rolled steel beam. So you can see that this is the beam, and that is fixed support at the end, and there is a load of 10 kips at point E. From point A to C there is a uniformly distributed load, that is 3 kips per feet, and total it is acting on a length of 8 feet. So we will solve this problem by using another method. Now in this method we will section the beam at any point, and we will take that distance as x. X can be any distance from this point A along the length. So let's solve this problem. Now you can see in this problem this 10 kips force is given at point E. So in order to convert, or in order to move this point E to point D, so this force will be 10 kips, and there will be a moment as well, and this moment will be equal to 10 into 2 feet, which is 20 kips into feet. Clear? So if you provide this, if you move this force to point D, and you also provide a reaction couple or a couple, so you can replace this 10 kips with this one. So if you write this, so then there will be no need to represent this. Okay. So solution, the steps of this solution is that first of all we have to replace this 10 kips kips force to the point D with a force and a couple system at D. And then we have the second step is then you have to replace this reaction support, so there you will find RB and RB X and RB Y. Clear? And there will be a moment as well at reaction point, that is MB. So you have to find this RBX, RBY and MB at point C by using equilibrium condition. As there is no force in X direction, so we take this X is RBX is equal to 0. So only force in vertical direction and movement. So you can calculate this RB and MB by using equilibrium condition. So if let me explain a little bit later, you will also solve this by yourself. So if this is point B, so this is the reaction force at point B, and there is a moment M. At point D there is a force of 10 kips, and there is a moment that is 20 kips into inch, and also a uniformly distributed load at point, this is point A and this is point C, this is point D. So this is W. Now in order to find this reaction force, you have to convert this uniformly distributed load into concentrated load. So you have to multiply this W with total entire length where this uniformly distributed load is acting. So it is 8. So W into 8. W is 3 kips. So it will be, if you want to convert this uniformly distributed load into concentrated load, so we have to multiply with W with its length. So 3 into 8 is 24. So it will be a 24 kips force, and it will act at a distance of half of the length, which is 4. Clear? So this distance will be 4 and this distance will be also 4. Also this force, this moment is given, so now you can apply sum of all force along y direction is equal to 0. So you can see you have 24 kips force acting downward, you have 20 kips force acting downward, and their reaction force. So by using this equation you can find out the reaction at point B. Now you can take the moment at point B is equal to 0, and you can find out these reaction moments by using this equilibrium condition. So kindly solve it by yourself. I will move forward. It's very easy. I have given you some idea, and one more thing, that it is very basic thing, and you must understand how to find out the reaction forces or reaction movement, because it is the first step of the problem. If you have any problem in calculating this reaction forces or movement, then you cannot be able to move on further. So first clear your idea regarding the equilibrium conditions. Then we will take, after finding the reaction forces, we will take the sections at different points, section the beam at point near the supports and load application points, and then apply equilibrium condition. For example, this is the load point, so you can cut the section over here. After the load application you can take a section over here, and after the support you can also load section here. So basically in this problem we have 3 sections to be analyzed, and in each section we will draw its free body diagram and then apply the equilibrium condition in order to find the shear forces and bending moment. And then when you get the shear force and bending moment at point 1, section 1 shear force and bending moment, at section 2 shear force and bending moment, and section 3, so then you have to draw the shear force and bending moment diagram, and from that diagram we can find out the maximum bending moment. When you get the maximum bending moment, you can calculate the maximum normal stress by using formula sigma m is equal to m over s, or mc over I. Clear? So this was the part first. Now in part second it is given, find out the stresses before the point D and after the point D. So we will see from bending moment diagram we will find the stress before the point D and stress after the point D. So let's start with the solution. So first of all, the free body diagram of the beam must be drawn. So here it is drawn, the free body diagram. So you can see this was the reaction force that you have to find, and after calculation it comes out to be 34 kips, and this was the reaction moment that comes out to be 318 kip into feet. Rest all things are same. So this is point D where 10 kips force is applied, and a couple or moment of 20 kips into feet. So from point A to C we have 3 kips into feet. So let me write down the distance from A to C. It is 8 feet. This distance is 8 feet. From C to D it is 3 feet. From C to D it is 3 feet. From D to E it is 2 foot. Or from D to E it is 2 foot, feet or foot. And from D to B it is 5 feet. That means this is 5 feet. Okay. So first of all you have to replace that 10 kips with equal force couple system that is shown over here, that is 10 kips force and 20 kips force. Then you have to find the reaction and the moment at point B, which you will calculate, and after calculation you will come to know that reaction force at point B is 34 kips and moment at point B is 300 kips into feet. Now we will cut the beam at any section after the application of load. So you can see at point A there is no concentrated load, but between section A and C there is a uniformly distributed load. So you can take the section at this point 1. Let this is section 1. So if you analyze the beam of the left section of left side, so this was the beam, this is the beam that is shown here. So if you cut the beam, so definitely there is a shear force that will be in downward and the reaction movement M. So, and this, let this length of the beam where we cut is denoted as X. Clear? Now there is a distributed load. Now this distributed load is 3 kips per feet and the length is here X. So if you want to convert this uniformly distributed load into concentrated load, so you have to multiply this 3 with X. So it will be 3X and it will be acting in the mid of this section. Clear? So total is X, so this distance will be X by 2 and this will be again X by 2. Now you will apply the equation of equilibrium equation. So sum of all forces along y direction is equal to 0 and upward is taken as positive. So you can see there is a force that is minus 3x that is acting downward and minus v which is acting downward. Their sum must be equal to 0. So v will become equal to minus 3x. Now this is for the region when x is greater than or equal to 0 and this x can goes to length 8 feet. You can cut the beam between 0 and 8 feet length. So this is the shear force equation for the section for the length of beam AC, which is 8 feet. So you can cut it over anywhere. Now you have to find the moment. Now this moment at point 1. So sum of all the moment at point 1 must be equal to 0 and counterclockwise is positive. Now you can see there is a force that is acting. This force is 3x and it is producing movement in counterclockwise. So 3x, and what about this distance? This distance is remaining perpendicular distance is x by 2. So 3x into x by 2 plus this moment, their sum must be equal to 0. So moment will be equal to minus 3x square over so minus 3x square over 2, or it is equal to minus 1.5 x square. So this is the bending moment equation. M is equal to minus 1.5 into x square. And this bending moment equation will be valid for x is greater than 0 and less than 8. So for x is greater than or equal to 0 and less than or equal to 8 feet. Now we are going to take the section at this point. This is section 2, and if you represent the free body diagram, so it will be like this. This is the beam. So if you cut the beam, so there will be a shear force and the reaction moment at point 2. So let this is point 2. You can see that on the left of the beam of this section, so there is a uniformly distributed load, and this uniformly distributed load from this point to this point, this distance is 8 feet. Clear? So in order to convert this uniformly distributed load into concentrated load, so this load is 3. Clear? And let this distance is cut at a distance of x. Clear? Now this load is acting over the length of 8 feet. So 8 into 3 is 24. 8 is the length and 3 is uniformly kips per foot is the load. So 3 into 8 is 24. Now this 24 kips force will be acting at the mid. So from this point to this point it is 8. So this distance will be equal to 4 feet. And this, from this point to this point, this distance is also 4 feet. Also from the start till the point 2, total distance is taken as x. Clear? So remaining this from the load from this point till this distance will be, this is 4. So this distance will be x minus 4, which is represented over here. So we will again apply the shear force equation at point 2 and bending moment. So now you can see that shear force at point 2 is, there is a downward force that is minus V, and again this force, concentrated force, which is negative, which is 24 kips, and there is no other force. Clear? So that their sum must be equal to 0. It means that V is equal to minus 24 kips. There. Now we have to find this moment at point 2 as well. So sum of all the moment at point 2 is equal to 0, and counterclockwise is taken as positive. So you can see at point 2 there is a moment m that is in counterclockwise direction. So that is plus, and due to this concentrated load there is a movement that is also in counterclockwise direction. So its magnitude will be 24 times perpendicular distance, and this perpendicular distance is x minus 4. So plus 24 into x minus 4 is equal to 0. It means that m is equal to minus 8 plus 96, minus 8x plus 96. So again this is not 2, this load is not 2, this is 24. So let me clear it. So this is 24, let me write it again. So this m will at point 2 will be minus 24x plus 96. So this is the moment equation for what? For x is greater than or equal to this at point C. This distance is 8. X should be greater or equal to 8 and less than this point is, this is 8 and this is 3 feet. So it is total 11. So x should be greater than 0 and less than 11 feet. Clear? Similarly, you can, let me delete something from the screen. So again it is also solved. You can see now that if we section at point 3, so the figure is given over here. So let the distance from the starting to the section 3 is x, and the load, uniformly distributed load acting on length of 8 feet is given, and at point D there is a 10 kips force and 20 kips feet moment is given. So by using equilibrium condition you can solve it, and you can also find the equation of shear force and bending moment. It's very easy. So for shear force, the now shear force will be equal to sum of all forces along y will be equal to 0. So it will be minus V minus 24 and minus 10 is equal to 0. So V will be equal to minus 34 kips. And you can also find the bending moment equation at this section by using the equation sum of all the moment about point 3 is equal to 0, and it will yield you a equation for the bending moment through this region. So I clear it, I remove all the writings. So now you can see from A to C, it means x is greater than or equal to 0 and less or equal to 8 feet. So the shear force is 3 into x minus 3x and minus v is equal to 0. So v is minus 3x kips. And this moment m, this is clockwise, so plus m into this force is producing movement again in clockwise. So 3x into perpendicular distance. So if you calculate it, this is the equation of bending moment equation for x is greater than 0 and x is less than 8 feet. Now for section 2, we have, when you apply the equilibrium condition, so you will have v is equal to minus 24 kips. How? And I have explained it earlier. So v, you can see there is a v shear force v that is acting downward, and there is a force minus 24 kips. So this v will be this one, and the moment equation is 96 minus 24 x in kips into 8. I have explained it. Now if you take the third section, so again if you take the third section and you apply the equilibrium conditions, so you will get the shear force is minus 34 kips, and you will get an equation for bending moment, that is 226 minus 34 x kips into Newton. Now this is for x is greater or equal to from D to B. So from D to A, this distance is, this is 8 and this is 3. So 11. So x is greater than 11 and less or equal to, total is this 5, so 16. Clear? And similarly from C to D, so x is greater or equal to 8 and less or equal to 11, because D point is at 11 feet distance. So this is the bending, this is the shear force and bending moment equation for x is greater than 0 and less or equal to 8 feet. This is the bending moment shear force equation and bending moment equation for x is greater than 8 feet and less than 11 feet. And this is the shear force and bending moment equation for x is greater than 11 feet and less than or equal to 16 feet. Now we will plot them, or we will draw the shear force and bending moment diagram for the above beam under the given loading. So now you can see this is the beam under the given loading. So you have to draw that vertical line from the ends, and then you draw the horizontal line in order to show that the length of beam varies along this axis x. Now let me write again. So we have v is equal to minus 3 kips, m is equal to minus 1.5 x square. So this is when x is greater or equal to 0 and less or equal to 8 feet. This was the first one. The second one is v is equal to minus 24 kips and m is equal to 96 minus 24 x into kips. And this was for x is greater or equal to 8 and less or equal to 11. For third, we have v is equal to minus 34 kips and m was 226 minus 34x kips into inch. And this is for x is greater than or equal to 11 and less or equal to 16. Now if you have all these equations, you can plot them. So first we will draw the shear force. So we will start from x is equal to 0 and less, x is greater or equal to 0 and less or equal to 8 feet. So at point A you can see there is no concentrated load. So definitely at this point the force, shear force will be 0. Now by using this equation, this is actually 3x. Again if you put x is equal to 0, so this force will be at this point will be 0. Now at x is equal to 8, let another point is x, which is 8. Clear? So you have to multiply, you have to place x, you have to place 8 instead of x. So 3 into 8 is minus 24. So if you draw it according to the scale, so and locate minus 24, let this is the minus 24 over the length or at point C or over the distance of 8 feet. So this is 8 feet. Clear? So you have minus 24. Now, how you will know to join these 2 points? How? You can see that this uniformly distributed load is a constant load. So again, shear force will be 1 degree higher. And you can see that shear force is a 1 degree a linear equation, so bending moment will be a 2 degree. We will discuss it a bit later. So now you can easily join them by joining 2 points. Or if you are confused, you can take the value of x. You can increase the x. You can take x1. It will give you at a distance of 1 feet. It will give you some point. Again at 2, it will give you some point. And again 3. So you can, if you join all them, you will get a straight line. So see, this is the shear force between section A and C. Now we will move at section 2. For section 2, we have shear force is equal to minus 24 kips and x is greater than 8 and less than 11. So it is a constant number, so it means from 8 to 11. So this distance from this to this is 8 and this from this to this is 11 feet. So from 8 to 11, only shear force is minus 24. So this again, this point will goes on. This is a constant line, constant value. Clear? Now at point 3 or section 3, you can see that from C to D it is constant, but immediate after point D there will be change in the shear stress. So you can see from point D we have minus 34 when x is greater than 11 and less than 16. So x is greater than 11 and less than 16. This is the region. X is greater than 11 and less than 16. So you can see the shear force is minus 34. So it means that you have, this is minus 24 and you again will go to 10 more downward. So from this point to this point, this total is minus 34. So this will be the point. And again from x is greater or equal to 11 and less or equal to 16. Until 16 it will be the same constant value. There, so this point is again minus 34 kips. One more thing is that the end of the beams having shear force will be the same in the shear force diagram. So you can see at the end of this beam there is no concentrated load, so shear force at this point is 0. Again at the end of this beam there is a force 34 kips, and in the shear force at the end there is 34 kips. Although the sign is different, but their values will be the same, and this will show you that you are going in a in an accurate track. So you are going well. There is no error in your problem. Here, so this is the shear force diagram for the given load. Now for bending moment diagram, again we will draw the horizontal line between the end of these two beams. Clear? And we will use these three equations. So let's start with first equation. So now m is equal to minus 1.5 x square. Now x is greater or equal to 0 and less than or equal to 8. So if x is equal to 0, so moment at this point will be 0. Now at x is equal to 8, if you multiply 8 with 1.5, clear? Sorry, if you not with 1.5. Okay, if you if you take the square of 8 square, that is 64, and multiply by minus 1.5, it will give you minus 96. So again you have to plot or locate the minus 96 at point B. So according to your scale, chosen scale, you will identify the minus 96 at point B. So let this point is minus 96. So now these are the 2 points. So how you will join them? So you will see that this shear force is a linear equation. Clear? So definitely the bending moment will be a curve, or it will be a parabolic. But here it is drawn like this one. Why it is not drawn like this? This one is in clockwise direction and this one is in counterclockwise direction. So I will explain this. Remember that if the shear force is a linear equation or a linear curve or a linear line, clear? The shear force is a linear expression or it is a linear line and it is in going downward or the slope is going downward. So the moment will be again taken as clockwise. So you can join point 1 and point 2 in clockwise direction. If it is like this, then you have to join them. I have just write this line or drawn this line as per understanding, but it's not correct. Depending upon the situation, if this line, linear line, is like in upward direction, or slope is in upward or increasing direction, so then in that scenario this parabolic will be like this one. I hope it's clear. Again I will repeat that you will look to the shear force diagram, and if in the shear force diagram, if this line, linear line, is going toward downward or slope is decreasing, clear, or slope is in downward direction, so in bending moment the curve will be in clockwise direction. Clear? Or if you are confused, you can use this formula. You can put the value of x is equal to 1, so at one distance or 1 feet length you will get the value of m. At x is equal to 2 you will get another value. So definitely you will join these points and you will curve like this. So this is the bending moment diagram between section A and B, or x is greater than 0 and less than equal to 8 feet. Now we will move toward from section C to D, which is x is greater than 8 and less or equal to 11. So you have this equation, bending moment equation. So if you put x is equal to 8, so again this will be 24 into 8, and again it will be the same, minus 96 keeps into 4. And if you put x is equal to 11, so you will get minus 168 keeps into feet. Clear? So you have to locate minus 168. Let this point is minus 168. Now how to join? So you will look the shear force diagram. Now you can see shear force diagram is a constant number or a line with zero slope. So definitely bending moment is line will be 1 degree higher, so it will be a linear line. Now we will move toward from D to B. So our x is greater than 11 unless or equal to 16. So if you put x is equal to 11 in this equation, so you will see that the bending moment will be minus 140. So this will be minus. So it means that bending moment is now shifted toward from minus 168 to minus 148. And if you put x is equal to 16, so it will give you 0 bending moment. So this point will be 0. Again, this is a 0 degree line or a constant number, so the bending moment will be a first degree line, or it's a linear equation, so you can easily join them. So this is the bending moment curve or bending moment diagram. Now you can also see that the area under the shear force, which is AEB, this is a triangle, and the triangle area is equal to half of B into H. B is 8 feet and H is minus 24. So if you put 8 and h is minus 24 and take half, so you will get minus 96 kips into feet as movement value. Again, this area is a square one, so 11 into this total distance 24, it will give you the movement under the value of movement, which is minus 168. Clear? Okay, and similarly so on, you can check it as well. Now, we have solved the first part of the problem, in which we have been asked to find out the shear force diagram and bending moment diagram. In second part, it was given to find out the stress before point D and after point D. So from shear force diagram, you can see that this point, at this point, this is point D. At this point, the moment at this point, actually this area shows you the left side, and this point show you the right side. So you have to find out the stress before point D and after point D. So we have moment before point D and after point D. So we will put in the flexure formula in order to calculate the stress before point D and stress after point D. So apply elastic flexure formula to determine the maximum normal stress to the left and right of the point B. Now we know that stress is equal to MC over I, or stress is equal to maximum stress is equal to M over S, where M is the bending moment and S is the section modulus. So section modulus for this wide flash 10 into 120 roller beam, if you go to appendix C and you locate this beam, so S is 126 inch cube above x-axis. Clear? So S value is taken from the table. Now to the left of D, this moment is 168. Neglect minus because it is mod. We have to find the stress, maximum stress before point D and after D. So you have to take this value 2016 kips into inch. Now this moment before point D is mod is 168 kips into feet, and you have to convert it into kips into inch. So 168 into 12 will be equal to, because 1 feet is equal to 12 inch, so that will be kip into inch. When you multiply 168 with 12, so you will have 2016 kips into inch. Because why we are converting from foot to inch? Because the S value is in cubic inch. Here, so for consistency in unit, we have to convert this. So when you calculate it, sigma m before the section or before the D point is 16 ksi. Now to the right of D, this is the moment is minus this 148. So if you again multiply 148 with 12, so it will be 1776 kips into inch, and divided with section modulus, so you will have maximum stress at after point D. So this was all about sample problem 5.2. I hope you have learned it.